Hello, class. All right, so we're going to talk about an ideal gas, and we're going to look at it from a microscopic point of view. So earlier, we had the ideal gas law, which we can write in two different ways. They're equivalent, of course. In this notation, the lowercase n is the number of moles, and the uppercase n is the number of particles. And we came up with this law by combining the results of several experiments. So for an ideal gas, the macroscopic properties, like pressure, volume, the amount of the gas, and the temperature, those are the four macroscopic properties that kind of define the state of the gas. And there were various experiments where you'd hold, say, two of these variables constant, and then there remains two other variables, so you can vary one and see what effect that has on the other variable. And so there were a series of experiments that were done historically that have names like Charles' law and Boyle's law and Avogadro's and Gay-Lussac, I think, were the main experiments. They kind of led to what we call the ideal gas law. Now we want to look at, and again, they came about with this law before the atomic theory of matter was fully known and accepted. There was major scientists who objected to the atomic theory of matter even in the early 1900s, before 1905. 1905, that was kind of the year that Einstein published a paper on Brownian motion. That was kind of considered the end of the debate about atoms. But anyways, so now we want to look at what's going on a microscopic level. And we're going to consider, say we have a box or a container, and for simplicity, we're going to consider this to be just a cube. That'll make life a lot easier for us. And we're going to consider molecules moving around inside this cube. And we know that when they collide with the walls, they're going to exert force on the walls. And that's where the pressure comes from. All these collisions with the particles hitting the wall. So let's say we have our wall here. And say a typical particle comes in, hits the wall, could be, it could hit an angle, most likely it will. So it has a velocity v, and it's going to bounce off of the wall. We can call that v prime. We have like a before and after. Now, we're going to make an assumption here, and we're going to assume that the collisions with the wall are elastic. And if particles collide with each other, those are also elastic collisions. So there's a collision here. So the particle is going to exert a force on the wall is going to exert a force on the particle, and those forces are going to be equal in magnitude by Newton's third law. So let's just look at the magnitude of the force as the result of a single collision. So let's say F1, that's a result of the force on the wall due to the collision with a single molecule that has a mass m, and it moves with a velocity v. Now, we're going to look at the x component of the velocity. That's what's pushing outwards on the wall. We can break this velocity into x, y, and also a z component, which we can't really draw, but it's there. And only the x component is going to exert this outward force on the wall. And so the force, I'm going to write it down first. Well, here. From Newton's second law, force is equal to the rate of change of momentum over time. And the change in momentum is going to be 2mvx. And delta t is the time of the collision, which is going to be very short. It's going to hit the wall and bounce right off. So delta t is a very small value. Now, if we were to plot this force, I'm going to do it over here. Let's plot this force as a function of time. And we're just looking at a single particle here. And the force as a function of time might look something like this. You know, typically the force is 0 until there's a collision. You know, if the molecule is significantly far away from the wall, it doesn't exert any significant force on it. And of course there's things like gravity, but they're completely insignificant. But when it hits the wall, there's going to be a relatively large but very short duration force. And then it's going to bounce back, and it's going to, you know, maybe bounce off a few more walls in the process, but then it's going to hit the wall again at some later time. And let's define capital T to be the average time between collisions. So basically, let's look at a special case. Say the particle is just moving straight in. It's going to hit this wall, bounce back, hit the next wall, and then hit it again. And it's just going to keep bouncing back and forth. So that t over there would be the time it takes to go hit this other wall. So it's going to go here, hit this wall, and then bounce back. And the time it takes to make that round trip, that's going to be t. All right, so this is a very irregular force. If we're just looking at a single molecule, it's bouncing around. And what we want to do is, let's define like a long-term average of this force. We can take the average over one period, the back and forth time, or at least the average value. Or again, if you just took like a long-term average, like long compared to the time of the, or long compared to that period, then the average force, we'll still call it F1 average because it's, you know, one particle bouncing around. That would be 2mvx over capital T, to the time between collisions. So the average force, I'll use a different color for this. Let's say this would be the average force. It's going to be much lower. Now, clearly the average force is not a good representation of what is going on here. Make sure that's in the picture. All right. Yeah, and the actual force due to this one particle, you've got these spikes, and then it's 0, and then another spike, and then 0. The average force does not resemble this at all, but it is an average. And the reason why this is actually a good representation for what we're doing here is because we're going to have an enormous number of particles bouncing off these walls. And so, yeah, if we were to draw another particle, we'd have a picture similar to this, but it would be offset because, you know, they're not moving in sync, they're moving randomly. So we'd have a similar picture that looks like this. And, you know, if we take the average, it would, you know, it would look similar to that. Thinking we could have like added the two forces and then, you know, stack the second average on top. And then we had a third particle, we get another pattern like this. We have an average force, and you know, if we add it all up, this average force is actually going to be a really good representation of what is happening. Like say you have a tire, like say a bicycle tire that is at high pressure, and say you put a hole in it so air wants to rush out, but you put your hand there to block it, and so there's no air escaping, but you might feel that pressure pushing against your hand, but you're not going to feel it like a bumpy kind of thing with individual molecules constantly hitting you. There's too many collisions to notice this internal, individual molecules colliding with you. And so this average gives us a very good representation when you have a large number of particles involved. All right. And so the net force then, we would multiply by the number of particles. And let's say that capital M is the mass of the gas. That would be the mass, like lowercase m would be the mass of a single molecule. And n is the number, so if we multiply those, we get the mass of the entire thing. We can substitute that in here. But let's look at T. Now, if we look at this original molecule bouncing back and forth, it's hitting at an angle. And so it has this y component. So basically, it's going back and forth, and it's moving upwards vertically. Eventually, it's going to hit the roof, and then it's going to be moving down vertically. But the time it takes to make this round trip has nothing to do with the y component of the velocity. That's just moving vertically. The back and forth trip is horizontally. So just use it like, you look at the total distance traveled. That would be, let's say that the velocity in the x direction, that would be the total distance traveled, which would be 2d over the time it takes to do that, which we defined as capital T. So 1 over t is Vx over 2d. And let's plug this in here. Going to run out of room here. So I'm going to replace this with capital M. That's the mass of the entire gas. And then we'd have Vx squared divided by 2d. And the 2's are going to cancel out. So, let's just note that is the pressure, that's the force, the average force exerted on one wall of the box. Okay, now the pressure would be the force over the area. And the area is d squared. So if we multiply the net force by d squared, the 2's are going to cancel out. We'll have a d squared and times d in the bottom, that's d cubed. That's the volume of the box. And I'm out of room, so I'm just going to write this down in one step. Where the 2's cancel. So we have m Vx squared. All right. I should have done this earlier, I suppose, but we're looking at a single molecule moving around. And these molecules have a distribution of speeds. And so when we go to the average, we have to look at the average velocity. No, this is a single particle. We don't have to worry about that. When we go to the net force, we have to replace these with average values. Okay, so we've got, Vx squared. All right, and I think we're good here, but we want to get rid of this Vx. We're just looking at the x component of the velocity. And if you have a particle, we're moving in 3 dimensions here. And so the velocity has x, y, and z components. So the magnitude of the velocity vector just from the definition, you square each component and you add them up. And the same result will hold true if we look at average values. Now we're going to make an assumption here. I'm going to write it down first and then talk about it. So again, we're looking at average values. And what we're saying is that the average value of the velocity in each direction is the same. Or the average value squared, or the average velocity squared in each direction is the same. Now, that just means that any given molecule, it's equally likely to be going in any direction. There's no preference to move one way or over the other. And so that's a reasonable assumption, that there's just no preferred direction, so these have to be equal to each other when we take averages. And so if we look at this equation above, I'm going to write the result here. You have to erase the word soon. But the average value of v squared, that's vx squared. The average value of vx squared plus the average value of vy squared, but that's the same as vx squared. So we can write vx squared plus vx squared, and then we can replace the average value of vz squared with vx squared as well. And so we can write, v squared is 3 times vx squared. And so if we plug that in here, we have m over 3 vx squared. V squared. So we replaced vx squared with 1/3 v squared. Now, totally out of room here. I might be able to cram one more equation in here. I think I made a mistake as well. I neglected something. What did I do? Okay, the f net here, mvx squared over d, and then we divide it by d squared. What I forgot to do is divide by the volume. Sorry about that. When we went to pressure and crossed out these 2's, we had mvx squared over d cubed, and d cubed as the volume. Now I'm writing volume a little differently, kind of with this tail at the end, because we have two v's here. We use a lowercase v for velocity and an uppercase v for volume. It's kind of hard to distinguish them when I'm writing them, just based on size. So I'm drawing the volume in a particular way. All right, so I'm going to erase this board, or this stuff here. We're going to like to use this board on the right for things we want to save. So I'm going to write the result. We can actually kind of change that a little bit. I think I'll just write it down this way for now. So pressure is 1/3 times the total mass of the volume, or total mass of the gas, divided by the volume, times the average velocity squared. Now, this average velocity squared, there's another name for that. That's VRMS. So we could write it as VRMS squared as well. What RMS stands for is root mean square. So, let's look at, say, just the x component of velocity. So, say you have a gas and you have a lot of different particles, and you just take the x component of the velocity, and say you want to find the average of the x component of the velocity. What you're going to find is that it's always going to be 0. Maybe in a real gas there'd be slight fluctuations around that, but basically it's going to be 0. And the reason why, to take an average, you just add up all the components. So we'd add Vx. We add that up, we find what Vx is for each particle, add them all up, and then take the average. And the reason that we're going to get 0 is because we're going to have just as many particles going to the right as going to the left. So we're going to be adding a lot of positives and a lot of negatives, and those two are going to cancel each other out because there's no preferred direction. And so the average Vx, if you just look at the x component of velocity, its average value is 0. That is not very useful information. And so to define a more meaningful, we want to still have some idea of how fast these particles are moving. And so the problem is that we have some moving to the right, which we'll say is a positive direction, some moving to the left, which is the negative direction. So the first thing we do is square all of our values, and that ensures that everything is positive. So step 1 would be to square them. And then 2 is take the average or the mean. However, when we square them, we're not dealing with velocities anymore. We're dealing with velocities squared. And so to get the units back where they're supposed to be, then we take the square root. So that's why it's called root mean square. RMS. When you have things that have positive and negative values, very often you'd want to take the average by going through this process. And so we could replace this with VRMS squared. It's different notation, but means the same thing. Okay. So what we see is, if we look at the pressure of the gas, this is the mass density, the mass over the volume. So if you, say, cram more particles into this container, its mass is going to go up, but if the volume, if it's like a rigid container, the volume is not going to expand, the pressure is going to increase. More particles, greater the pressure. And another way you can increase the pressure is to increase the speed of the molecules. And if they're moving faster, that's going to be a greater pressure as well. All right. And that speed of the particle, that's related to the temperature of the gas. So that's kind of what we want to get to. We want to compare what we have here. I'm going to erase this board on the left. Need some room to work here. Guess I'll leave the box. Not that you'll have trouble visualizing a box, but we'll leave it there anyways. Now let's take this, this result here, and let's multiply both sides by the volume. So we have P times V. It's 1/3 times the mass times the average velocity of the particles squared. Now, we also know that P times V, we can write this in two different ways. I'm going to write it this way. So we'll use Boltzmann's constant and the number of particles. Remember, T is the absolute temperature. And it has to be, measured in Kelvin, or technically another scale based on absolute zero, but T can never be negative. And so we can set these two equal to each other. And we can see there's a relation between the temperature and the RMS velocity of the gas. And so that's a very, very important result, that the speed of the particles depend on the temperature. Yeah, talk a little bit about that as well. So we've got the relation between the speed of the particles and the temperature of the gas. That was first worked out by a guy named Maxwell. Very impressive thing he did working this out. He did this in the 1800s. This guy Maxwell, we're going to talk a lot about him later as well. When we talk about electricity and magnetism. He was one of the greatest scientists of all times. Or maybe we should say greatest physicist of all times. When I say like one of the greatest, probably top 4 or 5. Like up there with Galileo, Newton, and Einstein. Very, very smart guy. But he worked out this theoretical equation for what the velocity should look like based on the temperature. And we're not going to try to replicate what he did. It was very beyond what we can do in this class. But I should have had this page marked earlier. There's a really nice experiment that checked it and confirmed Maxwell's theory on this distribution of speeds. So let me just move around until I can find this picture. Yeah, here it is. So I'm going to hold this up here. So this, basically on the left, you have that's an oven. There's a small opening where particles can come through. And so, outside of this chamber here, there's a very hot gas, and that narrow slit allows particles to come through. And then there's a cylinder here that has these grooves on it that kind of make an angle here. Like you can see, like one of the grooves is kind of listed. So like if the particle is just going to go straight, it would follow that dashed line. But if it hits that groove, if it hits the opening there, then it's just going to crash into the upper wall. But what you do is you spin that cylinder. And if you spin the cylinder slowly, like say the particles are moving at a particular speed, or actually, let's say you have a large distribution of speeds, but if you spin that cylinder at a particular rate, if a particle's going at just the right speed, it's going to pass through without hitting either the upper or the lower wall of that groove. Like if the particle's moving really fast, it's going to hit the upper wall, and if it's moving very slow, then because the cylinder is rotating, that lower wall is going to rise up and hit the particle, and so it's not going to make it through. And, it's not terribly difficult to find a relation between the, like how fast that cylinder is rotating, and based on the dimensions of the cylinder, like how fast it's rotating, and for a given rotation, what velocity of particle is going to make it through. So like if it's spinning at a particular speed, only particles of a particular velocity are going to go through. So a device like that is called a velocity selector. And this experiment was done, I think in the 1955. So Maxwell did this stuff in the 1800s. Late 1800s. This was like 60 or 70 years later before they could get this very precise confirmation. Actually, I think they have a picture in here as well. Yeah, and here's the result of that experiment. Like those dots are the experimental values, and the line is the Maxwell's prediction, and they agree extremely closely. So, yeah, Maxwell's basically his. He explained this distribution of velocities in a gas. But overall, it does depend on temperature. When you heat it up, things move faster. So we're not going to get too much into theory because it's very complicated, but there is a relation between the two. Now, we want to write this in a somewhat different way. I'm going to write, let's multiply both sides by 3/2. So here they cancel out. And, the reason we did that, now on the left, we have the average kinetic energy. Well, let's do this. I'm going to replace M. Here, let's do this. Okay. So remember, capital M, that was the mass of the whole thing, which is the mass of each particle times the number of particles. And so these n's are going to cancel out. And so what we have on the left is the average kinetic energy of a particle, which is 3/2 times the Boltzmann's constant times the absolute temperature. And this is a very important result. Again, we see that this connection between the molecules, like how fast they're moving, and the temperature of the gas. But this is actually part of something much bigger, which we're going to talk about a little bit later. But it's called the equipartition theorem, which is something that comes from a branch of physics called statistical mechanics. But basically, what this equipartition theorem says, it relates the energy of a gas or just a system to like what's going on inside. Like here, we're looking at particles bouncing around off these walls, and basically these particles have kinetic energy. But later on, we're going to say that there's other forms of energy that a gas can have. And like each kind of energy can contribute like a certain amount that depends on the temperature. We're going to talk about this equipartition theorem in a different video, but I definitely want to make a note of this. I'm going to actually rewrite this. Here, I'll put it over here in our... So instead of writing 3/2, I'm going to write 3 times 1/2 times Boltzmann's constant times the temperature. And then number 3, we're going to see later that 3 exists because this particle is able to move into a 3-dimensional problem. The particle can move in the x direction or the y direction or the z direction. So I think we'll leave it here for this video. But the idea is to kind of connect the macroscopic properties of a gas based on experiments measuring things like pressure and volume and temperature. And now we have a model based on what's happening microscopically. And these equations kind of connect these two ideas. So we're going to leave it here, but we'll come back to this result later on. So that'll be it for this one.